Now let's see part 3, dynamic behavior of elastoplastic model. In part 2, we use two elements. One is the elastic element and another is viscous element. But here, we will use all these three elements to create the system. Connect parallelly or seriously. First, let's see the plastic element. Is ideal rigid plastic element, or we say is Coulomb body. And the stress-strain relationship of plastic element is given as this. For this element, there's a strength. If the load is larger than the there's sigma 0 is the strength. If the load is less than this strength, then there's totally no strain occurred in the system. But if the load reached to this strength and the element develop continuously, is there a condition that the load larger than the strength? No, because if the load reached to strength means the element already failure. At this moment, we couldn't increase the load. Now let's see. The area inside hysteresis looms A0, and this value equal to 4 times the sigma 0 is the strength times the epsilon d. Epsilon depends on the load applied times. And this is the energy loss. In fact, the hysteretic form of the body dissipates energy, which is different from that of the pure viscous element. The equivalent viscous damping coefficient of the plastic element can be obtained when the energy dissipation of the steady state hysteresis is equal to that of the viscous element at the same strength condition. Then we do know for viscous element the energy dissipation value is equal to pi times the sigma s square over c omega. Then that's the area is of the Coulomb body. The energy loss of Coulomb body is equal to 4 sigma s times the epsilon. That's same. Then we can solve the coefficient of C. Viscous coefficient C just equal to pi over 4 omega times the sigma s over epsilon. Sigma s sigma s here means the strength of it. Or in the viscous system is the stress is the stress amplitude or load amplitude. Now let's see. We just use this element to create some elastoplastic model. This is the simplest one. Ideal elastoplastic element. A spring connect with Coulomb body seriously, and we applying the load on this system. And when we applying the monotonic load on it, first, is there any deformation? Of course. If the load is not larger than the strength of Coulomb body, then Here, there's no deformation. We needn't consider it. But there's a deformation. There's a deformation occurred in spring, or strain occurred in the spring. Then in the beginning, the strain will increase linearly due to the spring. At last, the load reached to the strains of column body here. Then is unlocked, and the strain develop continuously in column body. And for the whole system, the strain will develop continuously. And for the first part, the slope just equal to the stiffness of this spring. This is the behavior of the spring. Now we are applying the acyclic load. In the beginning, the load is not larger than the strength of column body, and is following the monotonic load in the beginning. It will increase. At last, the load reached to the strength of column body. Then the strain of system will develop continuously. Because it's cyclic load, the load will decrease. Then, if the load decreases, then the load will less than the strength of column body. Now the column body is locked. There's no strain occurred in the column body, but the spring has a strain because due to the reduce of the load. Then it will deform following the linear elastic rate E, following this rate. Decrease to 0, then increase in inverse direction. And when in inverse direction is reached to the strength of column body, is unlocked, and the strain will develop continuously. And then it will the load increase and increase to another in another strength. It will go on deform. Then it will create this shape. The hysteresis loom create this shape. Here, this point is the first failure point, and we do know how much is the stress. It's just equal to the strength of column body. But how much is the strain here? Because this point is just on the elastic line, then we can easily to calculate this value epsilon r. We define it as epsilon r just equal to sigma s over E here. And we define this is a reference strain of this system. Okay. Then here, how much of is this strain? It is equal to, because this is the total strain is epsilon, and AO is parallel with BC. Then OC just equal to OM minus O here. Is equal to epsilon minus sigma s over E. Is also epsilon r here. This point, we can get the value of it. or is just the length of AB. Now let's see. The hysteresis loop is parallel logarithm. Parallel logarithm. Its area is 4 times the sigma s times the length OC is epsilon minus sigma s over E. This is the total area, or is the energy loss is also equal to delta W. This area means the dissipation of energy. Then let's see how to calculate the elastic strain energy, W. It's the area of triangular BOM. It's easy to calculate. W just equal to half of sigma S times the OM. OM is just epsilon. Okay. Now we know delta W and W. We can calculate the damping ratio, Kc. The spring stiffness coefficient of the equivalent spring damping system, namely second modular, is E. E just in the beginning, namely modulars are from O to A, this part is just the slope of this line is E. But if the Coulomb element failure, and then the curves is from A to B. To any point we connect the point with O. Then the slope of this dashed line is just namely second modular. Is equal to sigma s. Is sigma s over epsilon. There's a correct incorrect. Not E, is epsilon. And this is the condition is that the load is equal to the strain sigma s, or epsilon reach to the reference strain. Corresponding equivalent viscous damping ratio Kc is calculated by this equation. Just now we can calculate. Before failure of the Coulomb body is behave like a spring or linear elastic material, then the damping ratio, there's no energy dissipation, then that damping ratio equal to 0. The condition is that strain less than reference strain. Or if the strain is larger than reference strain, that means the Coulomb body failure. Then will create hysteresis loop. The inside area is just the energy loss. Then we submit the equations. We use the equations. These equations we can calculate how much is the damping ratio. It's equal to 2 over pi times the 1 minus epsilon r over epsilon. The condition is that epsilon larger or larger than epsilon r. It can be seen that the hysteretic system composed of idle elastic plastic element is a variable damping system. Now from this equation we can find when epsilon close to infinite, the damping ratio tends to 2 over pi equal to 0.637, while the second stiffness tends to 0 and becomes a pure viscous element. In the calculation of the equivalent viscous damping ratio, the triangular OBM area is used when the elastic strain energy W is used. Here, BOM triangular. The area is the maximum of elastic strain energy. Now let's move to another system. We call it a viscoplastic element or Bingham body. A viscoplastic element system consisting of a linear viscous element here, in parallel with an ideal plastic element here, Coulomb body. This is called Bingham body. This is Bingham body. I saw it in the figure here. I give you. And the cyclic load, the stress-strain relationship of this system is controlled by plastic element. When load sigma less than strength, and the viscous element when sigma larger than sigma s, they have different behavior. The combined stress-strain relationship is shown in Figure C here. I give you which is the superpositions of the rectangle and two semi-ellipses. Here, this is a rectangular, and there's a two half ellipses. At this time, the energy consumption of the system consists of two parts. The first is the viscous energy dissipation of plastic element when load sigma less than the strength of Coulomb body, and the viscous energy dissipation when load sigma larger than strength. The damping consists of hysteresis damping and viscous damping, and the equivalent viscous damping coefficient can be determined by the area of hysteresis circle CEG. Now let's move to another one. It's a spring slider parallel model. A spring with stiffness E and a slider with strength sigma S are connected in parallel, and the mechanical model shown in the figure A is obtained. This is a Coulomb body, or we also call it a slider. Spring connect with slider parallelly. And the monotonic load, when load sigma less than the strength of slider, then this is locked, and the total system cannot have any strain or any deformation. Epsilon equal to 0. But when load sigma larger than strength, then the slider unlocked. At this moment, the total load stress divided into two parts. First is the applying on the sliders to overcome the strength sigma s. The left part is used on the spring, on the elastic branch spring, and this stress just equal to E times the strain in the whole system. Then we can write the constitutive relationship of it. Epsilon equal to sigma minus sigma s over E. Therefore, the stress-strain relationship of the spring slider parallel model is a rigid linear hardening plastic model, as shown in figure B. Here, let's see. In the monotonic load, under the monotonic load, in the beginning, the load is less than the stress. There's no strain, and the move from O to sigma s. When the load reaches to sigma s, it will develop as a spring deformation. The slope of this line is E. With cyclic load, it will create this shape, hysteresis loop, create from O, A, B, C, D, E, F, G, H, back to A. This hysteresis loop. And cyclic load, the stress-strain relationship is shown in the parallelogram shown in figure C. And its area is 4 sigma s times sigma minus sigma s over E. Here, let's go back to see the area of it. The large area can be divided into four areas. The same four areas. Then we calculate the area of it. We use OA times OC to calculate 1/4 area. Then OA is the strength. The length of OA is the strength of this slider, sigma s. And how much is OC? OC is the strain. The strain just equal to sigma minus sigma s over E. Then submit into it, we can calculate the value of it. This is strain, and this is this is OC, this is OA, and 4 times. Which represents the energy consumed by the external plastic slider. The corresponding elastic strain energy is W, big W, which is the area of triangular BOC. We know that OC is strain. We know how to calculate this value. And BC is equal to the total stress. Total stress is equal to sigma s plus E times the Epsilon. Then we can calculate this value. It's just equal to half of sigma total stress times the sigma minus sigma s over E. The elastic stiffness coefficient of equivalent spring damping system, namely second modular, is given as this. When the load is less than the strength of slider, then is the vertical line, OA, OE. And the slope of it is infinite. Here. Is infinite. But if the load is larger than the strength, then we calculate the namely stiffness using total stress over total strain. Total stress is sigma, and the strain we can calculate by this equation, sigma minus sigma s over E. Then we can rewrite it here is equal to E times the 1 over 1 plus 1 minus absolute value of sigma s over sigma. The corresponding equivalent dissipation damping ratio is given in these equations. Damping ratio before failure. Before failure, that means is from OA to OE. This before failure is just an elastic body. And there's no energy dissipation, then damping ratio equal to 0. The condition is that the load less than the strength of slider. But if it's larger, the load is larger than strength, then there's energy dissipation, and we can calculate using this equation, 1 over 4 pi times delta W over W. Just now we already calculate how much is delta W and how much is W. We just submit into the equation we can get here. Finally, the result is 2 over pi times the sigma s over sigma. It can be seen that when sigma tends to infinite, the damping ratio tends to 0, while the stiffness tends to E. The stiffness tends to E, and becomes a pure elastic system. The final one, bilinear hysteretic model. A spring with the stiffness E2 is connected in series with a slider with a strength of sigma s. Just now I will introduce this system. This system is then connected in a parallel with a spring with stiffness E1. This is the system. The composite system as shown in figure A is obtained, which is a bilinear hysteretic model, linear elastic, linear hardening plastic model. And the monotonic load here, and the monotonic load. The stress-strain relationship of bilinear hysteretic model is given as this. First, let's analysis. In the beginning, when we apply load on it, because the load will divide it into two branches, and in the left branch, if the stress is not larger than the strength of slider, the slider is locked, then there's no deformation in slider. We needn't consider it. Then the system tends to two spring connect in parallel. Then it will deform as a spring, but the slope is the sum of two spring stiffenings. Then E equal to E1 plus E2 as this. And after the stress in the left branch reach to sigma s, at this moment, the left branch cannot have a further deformation. not have it will have further deformation.